screen. All right. Does everything look good? Good. Awesome. All right. Thank you for the kind introduction. Before I begin, I'd also like to thank the organizers for the invitation to be here today. I'm really excited to be here to talk about endocrine regulation of skeletal physiology and calcium metabolism. And I'm doing that in the context of lactation. And so, as Annika just said, I have a PhD in endocrinology and reproductive physiology. And I come from a lactation physiology lab. And so my PhD was really focused on the mammary gland side of things and how serotonin plays a role in lactation-driven bone remodeling. And being able to come back and see some of the things from my that were relevant to my PhD work from a bone perspective, now that I've been in the bone world for about a year and a half, has been a lot of fun. So, all right. Let's see. Okay. So the first thing I want to talk about, what is lactation? Why is it important? So one of the hallmarks of mammals is the mammary gland and the ability to lactate, which is a product of more than 200 million years of evolution. Despite the importance and prevalence of this physiological function, the evolutionary origin of lactation and the mammary gland is largely unknown. The mammary gland may have evolved from sweat glands, sebaceous glands, apocrine glands, or some combination of all three. Lactation strategies and milk composition vary dramatically among mammals. Monotremes, or egg-laying mammals, do not have nipples. Instead, the mammary ducts secrete milk directly from the skin in association with hair follicles. Marsupials, such as the tamer wallaby, can perform something called asynchronous concurrent lactation, in which adjacent mammary glands can produce milk of varying composition to two different joeys of different ages. In humans, lactation is a beneficial process for both parent and offspring, providing nutritionally complete milk for the baby's growth and development, as well as immune protection for the infant. So the World Health Organization recommends exclusive breast milk for the infant's first 6 months of life, highlighting the benefit of breastfeeding to both members of the breastfeeding dyad. So during the perinatal period, the maternal body must provide the growing offspring with sufficient calcium. As I mentioned, lactation strategies and milk composition vary among mammals, and in humans, human milk has approximately 260 milligrams per liter of calcium during the first 6 months of lactation. And when taking into account average daily milk yield, this is approximately 200 to 210 milligrams per day, which is a very high calcium demand of the maternal body. And so in order to accommodate for this, there's a temporary demineralization of the maternal skeleton that happens, as well as a little bit of increase in renal calcium conservation. However, I do want to note that there is no increase in intestinal calcium absorption during lactation. So over the first 6 months of lactation, a human loses on average 6 to 10% of their bone mass. Rodents, on the other hand, lose between 20 to 30. And one of the most remarkable things about lactation and lactation-driven bone remodeling is the ability of the maternal skeleton to be completely restored after weaning. So there are two primary mechanisms responsible for this lactation-related demineralization of the skeleton. And these are osteoclast-mediated bone resorption, which is resorption of mainly trabecular bone, and osteocytic osteolysis, which involves resorption of both cortical and trabecular bone. Osteocytic osteolysis was actually first described in 1881, although it didn't gain much favor at the time, and it's been revisited more recently, but some people still view it with skepticism. PTHrP, or parathyroid hormone-related protein, which I will discuss more on the next slide, is secreted from the mammary epithelial cells into the circulation, which stimulates osteoclastic and osteocytic bone resorption from the skeleton. The free calcium released into the bloodstream feeds back to the mammary gland, where it activates the calcium sensing receptor on the mammary epithelial cells to promote transepithelial transport of calcium into milk, and inhibits further production and secretion of PTHrP into circulation. So PTHrP shares a receptor with PTH. It's very important for skeletal development as it regulates chondrocyte differentiation, and it does this in a feedback loop with Indian hedgehog. It's also important for mammary gland development and function. There are 4 different opportunities for female's mammary gland to develop, and those are embryonic, adolescent, gestational, and lactational. And PTHrP plays a role in all of these. Further, to tie it in more to the mammary gland, there is evidence that it modulates breast cancer. During lactation, the mammary gland secretes PTHrP into circulation and into milk. There's a considerable amount of PTHrP that is transferred into milk, but the reason is still largely unclear. And it also contributes to the renal calcium conservation that happens during lactation. And so over here is just a little schematic overview of what's happening during lactation. So suckling affects the hypothalamus and suppresses GnRH, or gonadotropin releasing hormone, which leads to lower estradiol levels. At the same time, the mammary epithelial cells secrete PTHrP into circulation. And this combination of low estrogen and high PTHrP levels acts synergistically together to drive bone resorption, and this ultimately releases the calcium into circulation. The first experiment I want to discuss today examined the role of mammary-specific PTHrP and the effect it has on bone mass during lactation. This group selectively knocked out PTHrP in the mammary gland via the beta-lactoglobulin promoter, and firstly established that PTHrP is not necessary for lactation, as the animals lactated without issue. So first here, bone mineral density was measured on days 4 and 11 of lactation, and the mammary-specific knockout mice lost significantly less bone mass than their control litter mates. Next, urine CTX and plasma osteocalcin were measured. And interestingly, there is a significant decrease in CTX, but no significant decrease in osteocalcin, suggesting the removal of PTHrP from the mammary gland lowers the maternal bone turnover during lactation. On day 12 of lactation, circulating PTHrP, calcium, and PTH were measured. There was a decrease in circulating PTHrP. However, there was no significant difference in calcium or PTH. And the data is not pictured on this slide, but I do want to note that the transfer of calcium to milk also did not significantly decrease, and pup growth was not affected. And so in the absence of mammary gland-derived PTHrP, plasma PTHrP levels are lower, bone turnover is lower, and bone mass is ultimately preserved. And this suggests that the mammary gland actively participates in the regulation of maternal bone loss during lactation by releasing PTHrP into circulation, to act as an endocrine mediator of bone resorption. So later, this group focused a little bit on estrogen and looked at what's happening in the role of low estrogen during lactation. Because lactation is marked by a decrease in estrogen, and estrogen is considered protective to bone. And in this experiment, the same group I just mentioned established that the combination of low estrogen and high PTHrP worked synergistically to contribute to the lactation-related bone loss. So on the left here are representative sections of the tibias of nulliparous or non-pregnant, non-lactating, normally cycling mice, pregnant mice, lactating mice on day 12 of lactation, which is around peak lactation. And then this time point here is 7 days post-forced weaning at that 12 days of lactation time point. And so when looking at the biochemical markers of bone turnover, CTX was significantly elevated during lactation compared with the nulliparous mice. At 1 week post-weaning, it had decreased to baseline. Osteocalcin levels fell during lactation and increased toward baseline 1 week after the cessation of lactation. And on the right here are graphs of the bone mineral density of the spine, femur, and total body in age-matched nulliparous animals, animals in late pregnancy, lactating mice at day 2, day 5, day 12, and day 18, and then finally the mice that were 7 days post-forced weaning. And at all three sites, the gradual decrease in bone mineral density that occurs over lactation can be seen, along with that restoration, the beginning of that restoration in bone mineral density post-weaning. So the next step in this experiment was to treat animals with either estradiol or pamidronate to inhibit osteoclast-mediated bone resorption from day 1 to day 12 of lactation. And neither of the treatments had much effect on PTH or PTHrP levels. Estrogen significantly reduced plasma calcium levels compared with the vehicle treatment, and milk calcium concentrations decreased significantly in mice treated with estrogen. Both estrogen and pamidronate prevented the increase in urine CTX normally seen during lactation, and osteocalcin levels decreased in response to estrogen and pamidronate. So most, but not all, of the bone loss that occurs during lactation is due to this accelerated bone resorption. An important trigger for bone resorption at this time appears to be the combination of increased circulating levels of PTHrP along with the decreased circulating levels of estrogen. And I'll mention this again later, but at the end of the study, this group postulated that menopause could represent an inappropriate reactivation of the physiology designed to provide calcium for milk production. And the reasoning behind this hypothesis was because lactation is the only physiological state of estrogen deficiency during a female's reproductive life. And so finally, this group wanted to see if they could recapitulate lactation-related bone loss under similar hormonal conditions in non-lactating animals. In this experiment, mice were treated from the beginning of lactation until they were harvested on day 12. The authors experimentally decreased circulating estradiol pharmacologically via leuprolide, which is a GnRH agonist, or by performing an ovaryectomy to remove the ovaries. Lactation conditions were then established by the administration of PTHrP. Bone density at the spine and the femur were measured via DEXA in all of the experimental groups at day 12 of lactation. Lactation led to a large decline in bone mineral density at the spine, which is to be expected. The PTHrP, PTHrP plus leuprolide, and PTHrP plus Ovex all caused a modest degree of bone loss, but not to the same extent as lactation. In the femur, on the other hand, the combination of the PTHrP plus the Ovex caused a decline in bone mineral density equal to that seen during lactation. And so systemic calcium and PTH levels were measured after 11 days of treatment. Compared with the placebo, lactation and Ovex were associated with a slightly decreased calcium level, and the combination of PTHrP infusion with Ovex was associated with a slightly increased calcium level. And then compared with the placebo, PTHrP infusion, PTHrP plus leuprolide, and PTHrP plus Ovex were associated with a significant reduction in PTH levels. And so, although elevated PTH and decreased estrogens in the circulation clearly contribute to bone loss during lactation, they are not by themselves sufficient to reproduce the full effects of lactation on skeletal metabolism. And so the question remains, what about the other calciotropic hormones? And I want to highlight this publication from 1998 that looked at circulating calciotropic hormones of postpartum females that had lactated for 0 to 1 months, 2 to 5 months, or 6 months or more. And these authors concluded that the patterns of change in calciotropic hormones over the postpartum period were independent of PTHrP, estradiol, prolactin, or lactation status, and were not associated with bone turnover markers. And so next I want to talk about some of the research that demonstrates osteoclast-mediated bone resorption during lactation. In order to determine the role of rank-L signaling in lactation related to bone turnover, this group treated lactating dams with OPG from the first day of lactation through day 12. The circulating levels of TRAP, P1MP, and osteocalcin were significantly lower on day 12 of lactation in the OPG-treated mice as compared with the saline-treated controls. Histological sections, this one shows a multinucleated osteoclast with the yellow arrow on the bone surface in the OPG-treated mice. And similarly, this image shows the presence of TRAP-positive osteoclasts here in the red staining on or near the bone surface on the tibial sections in, once again, the OPG-treated mice. I always show whole body here, but bone mineral density decreased in the femur, the spine, and the whole body over the first 12 days of lactation, but treatment with OPG prevented all bone loss. So then micro-CT was performed on the trabecular bone at the femur on day 12 of lactation. Trabecular BBTV, number, thickness, and tissue density were all significantly increased in bones harvested from OPG-treated mice as compared to the saline-treated controls. Another interesting point in this study that was noted was that treatment with OPG does not alter calcium metabolism. Serum calcium, PTH, vitamin D, PTHrP, and urinary calcium levels were unchanged at day 12 of lactation. And here are histological representations of the mammary glands of both the saline-treated and OPG-treated animals on day 12 of lactation. And you can see there is no difference between these two groups. Finally, OPG had no effect on pup growth or milk calcium content at day 12 of lactation. The final step of this publication, the authors hypothesized that dietary calcium intake might be sufficient to supply calcium for normal milk production, even in the absence of bone resorption. And one of the interesting things I'd like to note about this is that in this experiment, the lactating mothers tolerated either treatment to OPG or dietary calcium restriction alone, but close to half of the dams treated with both a low calcium diet and OPG died before day 12 of lactation. So dietary calcium restriction magnified bone loss up here at the spine. Once again, I only have the whole body pictured, but it magnified bone loss at the spine, the femur, and the whole body as compared with the mice-fed control mouse diet. But OPG treatment prevented bone loss in lactating mice on a low calcium diet. Pup weights were lower in the pups suckling on OPG-treated mice consuming a low calcium diet. However, the authors proposed that this was because the overall milk production was reduced in the dams that were treated with both OPG and had dietary low calcium. Bone turnover markers also demonstrated a reduction in both bone resorption and bone formation rates in OPG-treated mice on a low calcium diet. And so in terms of osteoclast-mediated bone turnover during lactation, bone loss during this time frame depends on RANKL signaling. And blocking RANKL signaling in lactating mice prevents bone loss, but does not disrupt milk production or maternal calcium metabolism, unless dietary calcium is also restricted. And now I want to talk a little bit about the osteocytic osteolysis. It has remained a little controversial whether osteocytes play an active role in calcium homeostasis and whether this cell type can remodel its bone microenvironment. And so in this study, the authors examined osteocytic remodeling during lactation. So lactation induces osteocytic remodeling that returns to nulliparous levels post-weaning. Electron microscopy showed that during lactation, the osteocyte lacunae enlarged and also had irregular borders indicating mineral removal, and that's depicted with the white arrows. Osteocyte lacunae images were also used to measure canalicular diameter, and an increase in canalicular diameter was observed in cortical bone from lactating animals, though no significance was achieved. However, there was a significant increase in trabecular bone. And osteocyte lacunar area was significantly increased in both cortical and trabecular bone during lactation as compared to the nulliparous or 7-day post-lactation groups. Next, this group selectively knocked out the PTHrP receptor in osteocytes. And In mice lacking this receptor in the osteocytes, there is a significant increase in TRAP-positive, or there was no significant increase in TRAP-positive osteocytes like there was with the wild-type lactating group. And so bone mineral density in both the control and the knockout mice, excuse me, over here is bone mineral density. This shows a decrease in bone mineral density, both the control and the knockout mice during lactation. And in the control mice, the osteocyte, lacunar area, and cortical and trabecular bone of the tibia both significantly increased during lactation compared to nulliparous mice, while lacunar area did not enlarge in the knockout mice with lactation. And so osteocytes, like osteoclasts, can remove their surrounding mineralized matrix. It's under the influence of PTHrP receptor signaling. And with this signaling, osteocytes can remove perilacunar mineral with lactation, and then ultimately replace it as a skeleton recovers post-weaning. And so while the mammary gland's ability to orchestrate calcium metabolism and bone turnover during lactation is remarkable, I think the most interesting part of this story is how the maternal skeleton regains this bone mass after weaning. So because lactation-related bone turnover is related to increased osteoclast activity, stopping this activity is essential to the recovery of bone mass post-weaning. And so on the left here are trap stains of trabecular bone taken from a nulliparous rat, and then similarly from a rat that was on day 19 of lactation, which the pups were removed on day 20. And you can see the osteoclasts are stained red here and are adjacent to the bone surfaces, and once again, the visual difference between the nulliparous and the late lactation animals. Further, osteoclasts were also visualized on day 19 of lactation, that same time point, and then 24 hours after weaning. So you can see the layer of osteoclasts with these arrows extending along the bone surface at this late lactation time point. And then this bone surface also has like a scallop morphology, which is typical of eroding surfaces. And in the section taken 24 hours after weaning, the osteoclasts here, indicated with the double arrows, are partially detaching from the bone surface. And so this demonstrates that rapid changes in the maternal skeleton osteoclasts immediately following lactation. And then these changes include the disappearance of most osteoclast ruffled borders and the retraction of the cells from the bone surface. And then finally, weaning is associated with transient hypercalcemia. So circulating calcium and PTH levels were measured in nulliparous and lactating mice, and mice on day 3, 7, 14, and 28 after forced weaning. So weaning led to this transient increase in circulating calcium concentrations and a simultaneous decrease in circulating levels of PTHrP on day 3. And the levels of both calcium and PTH returned to baseline by day 7 and then remained normal for the remainder of the 28-day period. And this is just another visual of what happens to the bone microarchitecture during these different reproductive states. And so here we have a nulliparous mouse, a lactating mouse, a mouse 7 days post-weaning, and then 24 days post-weaning. And you can see lactation is associated with trabecular thinning and perforation, and this trabecular architecture rapidly reverts back to that seen in nulliparous animals post-weaning. And so a transient increase in circulating calcium levels and a simultaneous decrease in PTH levels were observed upon weaning. The decline in PTH in response to the elevation of calcium may also contribute to the reductions in Wrangell expression, thereby helping trigger osteoclast apoptosis. And then finally, the last thing I want to highlight is that this process does not require PTHrP. First here, this group measured PTHrP mRNA expression in the bone during the post-weaning recovery. So weaning, similarly to the other experimental designs by this group, weaning was forced on day 12 of lactation, and the skeletal mRNA was analyzed with real-time PCR. So PTHrP expression increased in the bone through the first 7 days after weaning. And then after they established this, the group then selectively knocked out selectively knocked out PTHrP in osteoblasts. So here's the bone mineral content versus baseline depicted at the end of pregnancy, the end of lactation, and day 21 post-weaning. The knockout mice and wild-type mice experience identical changes in bone mineral content during the pregnancy and lactation and after weaning. The bone markers osteocalcin and P1NP increased equally in both wild-type and knockout mice during this post-weaning recovery compared with the pregnancy baseline. And so PTHrP is upregulated in bone during post-weaning skeletal recovery, and it's required to maintain adult bone mass and strength. However, osteoblast-derived PTHrP is not required for the skeleton to recover. And so this leads to a few conclusions. During lactation, the mammary gland orchestrates bone turnover via PTHrP to liberate calcium for milk production via osteoclast-mediated bone resorption and osteocytic osteolysis. Low estrogen and high PTHrP contribute to, but are not entirely responsible for this lactation-driven bone remodeling. This bone loss during lactation depends on RANKL signaling, and osteocytes have the capability to remove their surrounding mineralized matrix under the influence of PTHrP receptor signaling. Further, weaning is associated with a powerful anabolic phase of skeletal remodeling that starts immediately after the cessation of lactation. And this is associated with the reduction in RANKL and widespread osteoclast apoptosis, and it does not require PTHrP. And so a few other conclusions. One I like to bring up because this was the focus of my PhD work was perturbations of the serotonergic axis, which contributes to lactation-driven bone remodeling. So I do want to throw it out there that lifestyle and environmental factors can impact the bone recovery and the ability of the maternal skeleton to recover post-weaning. Further, there are a lot of questions that we have in terms of lactation-related bone loss and kind of long-term implications. One of the big questions is pregnancies that happen and lactation that happens before skeletal maturity, because this may impair bone accrual and peak bone mass, since that has yet to be established. Lactation-associated osteoporosis can also occur. It's rare, but the prevalence is unknown since it's not very common for pregnant women to get DEXA scans, and usually it's only noticed at if there is a fracture. And then finally, I really like this idea, and one of the groups that I referenced quite a bit in this presentation has this hypothesis that postmenopausal bone loss may be a relic of lactation. So parity and lactation have not been associated with increased risk of postmenopausal osteoporosis and may be protective, actually. And so they propose that it's maybe this like evolutionary template that the female body follows after the loss of estrogen associated with menopause. So this uncoupled bone turnover leads to bone loss, which is more prominent in trabecular-rich sites. And then finally, as I mentioned, this unbalanced bone resorption is driven by estrogen deficiency, which is the main link to menopause. And so with that, I would like to thank the Charles Lab, my current lab, as well as my former lab and my PhD mentor, Dr. Laura Hernandez, who taught me everything I know about lactation. It was fun incorporating pieces from both my PhD work and my postdoctoral work so far. And so I would like to thank everyone for your attention, and I will take any questions.